So in this video on resonance circuits, you'll be able to understand and see the derivation and the concepts with respect to bandwidth, quality factor, and two cutoff frequencies or half power frequencies. So at resonance, we know I is I max and the power is dissipated is given as I square R. That is I max square into R watts. So when the current I is equal to Im by root 2, taking the RMS value of current, the power dissipated becomes as substituting the value of Im or I is equal to Im by root 2, that is RMS value of power. So the power would become as Im square into R divided by 2. You can see it is half of the maximum power. I repeat, so taking I as Im as the maximum power, converting it to taking its RMS value, we get equation 2, which is Im is equal to P by 2. So one can simply rewrite equation 1 as Pm by 2 is the power when the current I is equal to IRMS by 2. Okay, so that means, so we have seen this graph. As frequency increases at one particular point, it reaches maximum, that is called as F0, and at that value we have maximum current Im. And as we further increase the frequency, the current reduces. And taking the value of current Im by root 2, thus IRMS of your maximum current, and we have seen that power is half. And you can see at this point we have two frequencies. Okay, so taking current as IRMS, we have two frequencies, one dot which is at the green color waveform, other and blue color, and if we extend the two lines, we note them as F1 and F2. So it's observed that there are two frequencies, F1 and F2, at half power. So why are saying half power? So when I'm taking, please understand, at resonance we have maximum current. So when you say half power, we have taking the current as the RMS value of current. So at RMS value of current, the RMS value of maximum current, the power is being half of your maximum power. At that value, we have two frequencies, which is called as cutoff frequency or half power frequencies. Right? So it's evident here that from this equation 2, the power is being divided by 2. So at this value of, what was our reason for this? Is because of we have taken RMS value of current. So at RMS value of current, we are getting two frequencies, F1 and F2, which are called as cutoff frequencies or half power frequency. So at these frequencies, the power is only one half of that of F0. So these are called as half power frequencies or cutoff frequency. Now, the ratio current by current of half power by maximum current, we get that as 1 by root 2. So we express in terms of decibels, that is 20 log 1 by root 2 is nothing but minus 3 dB. Okay, so therefore F1 and F2 are also called as minus 3 dB frequencies. The frequency range between half power frequencies is F2 minus F1, and this is referred as passband or bandwidth. That is, as we seen earlier, it is F2 minus F1. The sharpness of tuning depends upon the ratio R by L. A small ratio indicates a high degree of selectivity. So small ratio means it is very narrow. And the quality factor Q is given as omega naught L by R. So we know that omega naught is equal to 1 by omega naught G. Thus substituting that in the above equation, substituting this in this place, we get the equation as Q is equal to 1 by omega naught CR. So we have two quality factors formula. How we get the same answer? That is Q is equal to reactance by R, or reactance is same, reactance by R. That is 1 by omega C is also XC. That is XC by R or XL by R. So omega naught we know it is 1 by root LC. If I substitute this omega naught value in the above equation, we get Ohm value of Q in terms of just R, L and C. Right? So Q is equal to 1 by R square root of L by C. If you simplify by substituting this omega naught here, you get the Q, which is equal to 1 by R root of L by C. So selectivity is the reciprocal of Q. Selectivity of a resonance circuit is defined as the ability of the circuit to discriminate or distinguish between the desired and undesired frequency. It is defined as a ratio of resonant frequency to the bandwidth of resonance circuit. So let us see derivation of two half power frequencies. So we know impedance of the circuit is Z is equal to R only under resonance condition. Therefore at resonance V is equal to I max into R. So I max is given as simply V by R. This we have seen in the earlier video also. So this means that the current is in the circuit at half power frequency is I max by root 2. I repeat, this means that the current in the circuit at half power frequency is I max by root 2. So we have seen in the video earlier, right? When we draw a plot for series resonance, we get maximum current at F naught, and we take the RMS value of current of minus 3 dB of the current, right? At that time it cuts the graph at 2 points, F1 and F2, and we have seen that at that point of current the power is being half, right? This is in the video that we have seen that I max by root 2. So we have taken PMP is equal to I max into R, we get maximum power. Taking RMS value of current, we have landed up with the equation that PM is PM by 2 for I is equal to IRMS, that is Im by root 2. So we have seen this in the earlier video. So we substituting the value of I max in the above equation for V. So V is equal to I max by root 2 into Z. So at half power it is not R, it is still Z. Why? Because current is not maximum. So only when the current is maximum at F naught, thus your Z is equal to R. However, at half power you can see the current is lesser. So at that point of time we have two different frequencies. So those frequencies XL and XC are not equal, and the impedance of the circuit is Z. This is R plus XLI minus XCI. So that is why it's important that you have to write. You should understand here how we got Z here. So at half power, we have seen here in the diagram, at half power you can see we have different value of frequency F1 and F2. So these two frequencies XL is not equal to XC. Thus the circuit is still having R, L and C. It's not just R, it is Z. In this condition, this is at resonance. So at resonance, Z is equal to R. So substitute I max from equation 1. Here we get V is equal to V by R root 2 into Z. If we simplify further, we get Z is equal to square root of R. So at resonance, please remember, at resonance Z is equal to R. At half power, Z is equal to root 2 into R. So in general, Z as discussed is equal to square root of, using Pythagoras theorem, it is R square plus XL minus XC the whole square. So substitute the value of Z in the above equation and simplify further by removing the square roots. We get R is equal to plus or minus XC minus XL, XL minus XC, right? Now, in this shaded part, as we increase the frequency, so I am saying that XC is greater than XL. How? I repeat, in this shaded part, we can see that XC is greater than XL. How? So what is the formula for XC? 1 by omega C or 1 by 2 pi FC. What is the formula for XL? 2 pi FL. So you can see at smaller value of frequency, right, which will dominate? XC will dominate, whereas XL will be smaller. So 1 by small values, this side, this portion will be larger, and this portion belongs to XC. Thus, for smaller frequencies, XC is greater than XL. So thus, from the third equation, we assume a condition that for smaller frequencies, XC is greater. Thus, at F1, XC is greater than XL. Thus, rewriting the equation 3 is very important, as R is equal to XC minus XL. So we know XC is equal to 1 by omega C and XL is 1 omega into L. Now we are substituting omega as omega 1 because we are finding the formula or expression for omega 1 or F1. Thus simplifying by taking LCM, we get R is equal to 1 minus omega 1 square L into C divided by omega 1 into C. Or rewriting this, taking the denominator towards your left side, LHS, we get W1C. Simplifying this further, and we get a quadratic equation, right? So solving this quadratic equation, we have the form of a quadratic equation I've shown you here. So we get minus B. In this, what is B? B is RC. What is A? A is LNC. And what is C? C is minus 1. So substituting that, we get omega 1 as minus RC plus square root of B square, that is R square C square minus 4AC. So you can see here the value of A is minus 1. So minus becomes positive, right? So simplifying this further, we can write this equation as minus R by 2L plus square root of R by 2L the whole square plus 1 by LC radians per second. So this is for what we have seen until now for W1. Now similarly, if you see in this shaded part, beyond resonance frequency, XL will be greater than XC. So as you can see, as I increase the frequency further, so for higher value of frequency, you can see XC will be lesser. But whereas frequency is directly proportional to XL, thus it is greater. So 1 by greater values, it will be smaller, thus XL is greater than XC beyond F0. Thus rewriting equation 3, F2, at F2 or at omega 2, XL is greater than XC, thus XL minus XC. Which is the same step, substitute the value of XL and XC as omega L and 1 by omega C, and substitute omega as omega 2, taking LCM, we get omega 2 square LC minus 1 by omega 2C. Rearranging that, we get one quadratic equation, and solving the quadratic equation, we represent omega 2 as, this is a mistake here, this has to be omega 2 minus RC plus square root of R square C square plus 4 LC divided by minus 2 LC. And solving that, we get omega, I repeat, it's omega 2. Omega 2 is equal to R by 2L plus or minus root of R by 2L whole square plus 1 by LC radians per second. This is for omega 2. So we have seen two cutoff frequencies. We have seen quality factor and bandwidth. Right? We have understood at F1 or omega 1 XC is greater than XL, and beyond F0 XL is greater than XC, and these are the two cutoff frequencies. So subtract F2 minus F1, we get bandwidth, right? These two cancel each other, so we get 2R by 2 pi, 2R divided by 2 pi 2L. Or if we solve further, we get bandwidth as R by simply R by L or R by 2 pi L. So R by L is for with respect to F, and R by L is with respect to omega. So quality factor, as we have seen, it is omega naught L by R or 1 by omega naught C into R. So substituting the value of bandwidth that we have got in above equation, right? So we know omega naught is equal to bandwidth, right? So we can see a bandwidth is R by L, right? So this is R by is about 1 by bandwidth in this case. Thus Q is equal to omega by bandwidth, or bandwidth is equal to omega by Q. So this is how we can associate with respect to bandwidth, resonant frequency and quality factor. So thank you for watching the video. So please do subscribe the channel to enhance your knowledge further.